In this video, I'm going to demonstrate how you can simulate a ported loudspeaker enclosure using both the boundary element functions in AKABAK as well as the lumped element functions. Now, to begin with, I have made a drawing in Fusion, which is a simple ported cabinet. It's cut in half because we are going to use Symmetry to make it more computationally efficient. And in this cabinet, this cabinet has been exported as a step file and then meshed in external software, Gmesh in this case. So I am going to simply open this file. We're going to the Components tab, open Mesh file, click on File, Open, and here we have the mesh file. Now the scaling we have to set to 1 millimeter because AKABAK treats us as meters if not. And now we have the drawing. So I am going to make this just a tad bit bigger. Here we have the drawing. You can see we have the exterior of the cabinet. We have a flat disk driver here, and we have a flat disk here on the inside. In addition to this, if we look at the port this way, we can see right into the cabinet, while this way we can see that we're looking at some parts here. These are going to be our interfaces, which are important when it comes to subdomain modeling. Now, the first thing we want to do is that we are going to abuse symmetry. And because of that, we do not need these parts here, because these are going to be inside of the speaker anyways. So I can see here, this is tag 15. So I can remove this, and I can also remove this, tag 18. And I can remove this one, tag 6. Now we have removed this, and this is fine. The cabinet is ready for simulating, so we can just click Apply and then close. Now, the next part is that we are going to make multiple subdomains. We're going to create one subdomain for the inside of the cabinet. We're going to make one subdomain for the inside of the port or the base reflex vent. And we're going to make one subdomain for the exterior of the cabinet. So we go to subdomains, click on this, and this is going to be cabinet interior. And this is going to be an interior domain. So we can just click Apply and close this. And then we're going to create a second one. This is also going to be interior. This is going to be port interior. Click Apply. Now that's fine. And the last one is the exterior domain, which is with the outer part of the box. So we choose exterior, we just give it a name, and we call this, we can just call this exterior domain. And then click Apply. So now we have 3 subdomains, and to connect these 3 subdomains together, we need interfaces. In this case, we click on Interface, and we can call this interface inside of box, cabinet interior to port interior. And this one will go from, here we see subdomain 1 is cabinet interior, subdomain 2 is port interior. Now you can see here, subdomain 1 is where the normals should point into. If you remember the model from earlier, you could see that the normals of the interface of the part that is going to be our interface, they were pointing in towards the cabinet and in towards the port for the one that goes from the port to the exterior. So in this case, subdomain 1 is the cabinet interior, subdomain 2 is the port interior. Click Apply, close this, and then open yet another interface. And the second interface is going to be port interior to exterior. And here we do the same thing. So subdomain 1 is going to be the port interior, which is where the normals are pointing into. And then subdomain 2 is going to be the exterior domain, or exterior subdomain. So we can just click Apply. And now we have all the interfaces and subdomains that we need. So to begin with, we can choose Elements, Mesh File. So we can begin by modeling the interior. So here we choose Cabinet Interior. OK. Then, if we make this a bit bigger, we are in the Drawing tab. So the first thing we have to do is we obviously have to remove everything that's outside. So for example, this is not something we need. So that's 16. And here we can see this is 13. We can see this is 23. No, excuse me, it's 14. And this on the back is 1. And this on the bottom is 12. And this diaphragm, or this flat disk, which is going to be our diaphragm on the front, is 19. So now all the parts on the outside are removed. However, we still have the inside of the port left, as well as these 2 points, which are going to be our interfaces. So I have to remove these two. This is 22 and 21. Remove these. And then we also have to remove the inside of the port, which is 8. We can see here it's 8. Now we only have the interior of the cabinet. You can see we can still see the port, but this is only the exterior of the port, not the inside of the port, as the normals are pointing in to the interior domain of the cabinet. So that's just wonderful. Now we have this right. But we also have to keep in mind that this part is going to be our diaphragm. So this is not going to be a solid object. So this has to be defined by itself. So in this case, tag 20 has to be removed. And now we have only the cabinet. Click Apply. Now we can see we have the inside of the cabinet here. The second part is making the diaphragm. So cabinet interior, and we can just call this diaphragm back. And now we just remove, this was part, let's see here, and make it a bit bigger. This was part 20. So we can just unselect all and then click 20. And here we can see this. This is the diaphragm. Now, the problem with this is that now you can see it's solid. So we have to go to boundaries, have to make this driven. In this case, direction normal to surface is completely fine because that is, this is just a flat disk. It's not really the proper geometry for a driver, but for low frequency simulations, this is completely fine. So now we can see it has become red. We just clicked apply and close. And now we have the entire inside of the cabinet. We have a driver and we have the inside geometry. The next part is to make the port interior. Now this is very simple. We just choose port interior and then we go to the drawing and then we just find out the port interior is tag 8. So we just unselect all, click tag 8 and then apply. Simple as that. So here we have a port. You can give these elements names if you want to, by the way. I'm not doing it because I don't really see the need for this type of project, but in a lot of cases it can be a nice thing to do, especially if you're going to revisit the project a lot of times. So now we have the inside of the port, and now we can start thinking of the exterior. So now we choose exterior domain, click OK. And now we're just going to remove everything except the outside. So the outside is points, let's see here. The outside is 16, 14, 13, 1, and 12. So 12, 13, 14, 16. So 1, 12, 13, 14, 16. And here we can see now we have just the outside of the cabinet. So we can click apply. And now it's starting to look like something. So we also need the front of the element. This is just the back, basically. So we need to also model the front. And we just go to exterior domain again. And this time we can just choose this part. You can see here, this is 0.19, so we unselect all and then just choose 0.19. And then we have to choose the boundaries, driven, apply. So now this is the front and back of the driver, respectively. Now the final part is that we have to connect all these parts by using interfaces. So once again, we click on Elements Mesh File, and we choose the cabinet interior to port interior. This is basically the connection point from the inside of the cabinet to the start of the port. And for the drawing here, we are just going to look at this little piece here. And that is tag 22. So we just undo all of these, and then we just have this one. Click Apply, and you can see it's blue, which indicates that it is a interface. Now we do this once more for the port interior to the exterior. This is the end of the port, and then which goes out into the exterior domain. So in this case, we do the exact same thing. We just click on this, and we can see it's tag 21. Check all off, and tag 21. Click Apply, and close. Now we can see we have these two blue interfaces, and we can see that the normals should be the right way. They should be pointing into subdomain 1. In the case of the cabinet to the port, subdomain 1 is the cabinet, and we can see the normals are pointing into the cabinet. We can see right through it here. It's transparent from this direction. And the same goes for this part, where subdomain 1 is the port interior and subdomain 2 is the exterior. So now we got the box modeled, but as you can see, it's only half the box. So we are going to have to use symmetry. And using symmetry is a way to make the simulation more computationally efficient. So for example, in this case, I can cut the box in half and then I can just mirror it. And this will, and AKABAK itself can mirror it. And this makes the simulation quicker for a given amount of resolution, pretty much. So for example, here I can solve this quicker than if I had this same density of mesh elements and I model the entire thing. So to do that, I'm going to global and to BEM parameters. And for symmetry here, I'm going to go to symmetry and choose X. And now we can see we have a box. This box is now, this driver is somewhere between a 5 and a 6-inch driver in terms of the SD, the moving area. And this port is a 2-inch port. It's 51 millimeters or thereabouts. It's probably a little smaller because of the rough mesh density, which makes it a bit smaller than it actually is. So now we have our box. There's one thing we can do. It's not necessarily something you have to do, but I like doing it. And that is just go back to General and click on Components here and just add a wall impedance to the inside of the cabinet. For a lot of interior problems, I find that this is a good idea. So this is just going to be cabinet interior impedance. And this is going to have a damping applied to it. I'm just going to set this to 0.01. Click Apply. And then I'm going to go to the BM tab again over here. And then I'm going to find the element that's the inside of the box. In this case, we can see that I'm marking it, and it's this part, these elements. I'm going to double click on this and go to Boundaries. And I'm going to choose a wall impedance. So I click wall impedance. The reference is just the one I created now, cabinet interior impedance. Click on this, click Apply. And now we can see that the inside of the cabinet has become green, which indicates that it has an impedance applied to it. Now I can close this, and now it's more or less ready for simulation. But first we have to decide what we're going to observe. And in addition to that, we should probably also make a lumped element model. I'm going to show you that afterwards. But first, let's just have a look at what we can observe. So in this case, I am obviously interested in the frequency response. So I'm going to go to the Components tab and go to Observations, and I'm going to create a radiation polar. And now we can see that the standard direction is on the x-axis, while in this case we have this aligned with the c-axis. So this is just going to be the summed output of the port and the speaker. So for range here, we have both of these. We have diaphragm back and elements 12. I forgot to give a name to elements 12, but that's the front diaphragm. For parameters, we can just set this. This can just stay at 90 degrees. This is mostly a low frequency simulation, so there's not going to be much directivity here in any case. And we do not want this to be normalized. So we just click apply, and then we have to also decide on the identifier of direction. And in this case, it's on the c-axis. So anything that starts with the c will work. So let's just do cx. And here we can see that the on-axis is here on the c-axis in front of the speaker, approximately right below the woofer. So between the two elements, basically. Now we've done this, we can also make an observation of the fields. This can be pretty interesting. So we choose fields shell. Now we can see that this lies in the wrong plane. This is not really what we're interested in. What we're interested in is seeing the woofer and the port output and seeing how those two look, and not the combined output alone, which is what this would show us. So we go to shell, and here we can see direction is Y. We want to set it to direction, we want to set it to direction C, I believe. No, that's wrong. We wanted to set direction X. I'm terribly sorry. Direction X, like this. Now, one potential issue with doing this is that this observes the fields inside the speaker as well. And inside the speaker, the pressure will be extremely high, so we will see very low pressures outside of the box, which can be a bit annoying. So to just make the data easier to see, we're going to displace this one a bit. So in scaling of position, I'm going to click Edit, and shifting in X, Y, C. So I'm going to shift this in the C-axis, and I'm going to shift it by 500 millimeters. Okay, apply. And now you can see that the fields are in front of the speaker only. So I'm just going to observe how the output combines from the woofer and from the port in front of the speaker. In addition to this, we can make the delta here a bit smaller if we want. This is basically the resolution. Here you can see these squares. If you make the delta lower, if I have it, for example, you can see that you get more and tinier squares, excuse me. So I'm just going to set it to 0.35 here. That's probably plenty. And then I can just close this. So now we have some things to observe. Let's just try to make a simulation, first with fixed driving, and then after that, we'll look at how it changes when we use a lumped element model. So first now, we're going to go to global. We are going to choose frequencies, and we are going to simulate this box from 20 to 400 Hertz, for example. And 64 points, that's perfectly fine. That's 15 points per octave. That's not really a problem. Click OK. And there we go. And now we don't actually have to define meshing here. In the two earlier videos I've shown, you need to make AKABAK mesh because we're just importing a DXF file. In this case, the file is already meshed, as you can see. There's already a mesh here and plenty of triangles. So we're not going to tell AKABAK to mesh. It will still go through a mesh stage, which goes rather quickly. But if we don't set the mesh resolution to anything, then it's just going to keep this mesh. If we set the mesh resolution to be very high, then it's going to mesh this mesh over again, basically, to make it higher resolution. But we're not going to do that. So we don't need to do that, but we do have to set fixed driving in this case, since we have not made a lumped element model yet. And here we have to make sure a fixed driving is enabled, and we'll just choose constant acceleration again. So we click apply, but there is one trap you can fall into here, and that is both of these drivers, the inside and the outside, both of these are moving in their normal direction. And the problem with this is that it means they're moving in a push-push configuration rather than a push-pull configuration, which is what an actual driver does. When the outside moves out, the inside moves in, right? So we have to set the amplification here on the back diaphragm to -1. And now, when this driver moves in the positive C direction, the inside driver will also move in the positive C direction. So now everything is ready and we can run the simulation. So I'm just going to click calculate all. And there's a bit more elements than there were in earlier simulations. So this one is going to take a little more time, but it's not too bad. Just going to let it finish. So now it's doing the, now it's finished the boundary element part, and now it's doing the other parts. So here we can see the fields, and if we click on frequencies, we can see what happens. So we can see at 400 hertz, we can see that most of the output comes from the driver. There's not really much output from the port. The driver is where the output is from, and we can see that it's quite smoothly radiating in all directions. And then if we look at very low frequencies, say 20 hertz, here we can see that in the near field, there is plenty of output from both the port and from the driver, but they combine, and the resulting sound output is very low as you move away from the loudspeaker. Now remember, the fields we're observing here are only 1 meters in length. So the actual pressure, you have to be very, very close to get any meaningful sound pressure from the two of these. Now, if we go to, say, 70 hertz or so, maybe a bit higher, 70, 60, 68 hertz, for example, here we can see that it's the port that is dominating the output. This is where most of the output is coming from now. And if we go a bit higher in frequency, we can see that both of them contribute to the sound output almost equally. Now, if we open VAX, we can look at the frequency response. And this is the summed frequency response of the two. And here we can see that the tuning frequency is at approximately, I will say this is at approximately 70 hertz, right below, something like 68, 69, 70 hertz. But remember, this is with constant acceleration and does not really represent what it would look like with a real driver. We can see that it is relatively flat above the tuning frequency, and then it spikes up, and then it falls off as the two drivers start canceling each other. Now, if I go back, and go back into AKABAK, let us now do the modeling of the lumped element part to get a more accurate result. To do this, we click on the LEM part down here, and we can also click on the LEM part here. And we're going to go to the Components tab again, and here we can see we have a lot to choose from. There are a lot of menus here where you can choose all kinds of things. So what we're going to do is we're going to create a source, because we need a sound pressure, we need a signal for the actual speaker. And we're going to make an electrodynamic driver, which is here. And now this top part is the front output, and this bottom part is the back output. So what we're going to do, we're going to connect this, and then we are going to connect this part to ground, and then we're going to add two radiators, the front and the back. So this is radiator 1, and this is radiator 2. Now we go to radiator 1, and we can see here it says ref to BEM. So we reference this. This is the front diaphragm, which is elements 12 in our case. Click OK. And then for this radiation impedance, we go to ref to BEM and diaphragm back, which is the back. Now, here we need to specify the Thiel small parameters. I've already copied these from another project. So I'm just going to paste them. Assign to selected, excuse me. I'm going to paste them to all. And in this case, we have to also define the diaphragm front and diaphragm rear. In this case, diaphragm rear is diaphragm back here. Okay. And diaphragm front is elements 12. Okay. So these are the Thiel small parameters of the Purify PTT 6.5-inch woofer, the X version. I don't remember if it's the paper or the aluminum version, but it's just an existing woofer. So these are realistic Thiel small parameters, though the moving area of these radiators is not quite the same as for the Purify, so the results are not going to be quite the same. We can see here, if we go to diaphragm front, for example, we can see here it tells us the SD. So this is about 110 centimeters squared, as opposed to 132, 133 for the Purify woofer. So the results are going to be a little different, but the point is mostly just to get an idea of how you can set up this lumped element model. So now we have the lumped element model set up, so we can just disable the fixed driving. So we go to global, go to fixed driving, and we disable it. Apply, and that's fine. Now if we reopen the fixed driving, no, sorry, I'm thinking wrong, sorry. So we've disabled the fixed driving, so now it's going to be defined by this. Now we may be interested in, for example, setting a specific signal level. So to do this, we can go to global, and we can go to the level of driving. We can, for example, set this at 2.83, and then we can say that that's RMS. This would be equivalent to a 1 watt input into an 8 ohm driver. So now everything is ready with the LEM part. We can see we have a radiation impedance for both the front and the rear, or a reference to both the front and the rear, and a radiation impedance for them. And we can rerun the simulation. So we go to processing, we go to calculate all. Oh, excuse me, we don't actually need to recalculate because the boundary elements part has already been solved. So we actually only need to go to calculate individually. And then we can calculate spectrum, and we can calculate fields. And now for the fields, it looks mostly similar. We can see it's there's not really much that has changed here. The fields are more or less the same. It's still 400 hertz. The driver is doing most of the work. At say 105 hertz, they're both contributing quite a bit. And at 20 hertz, they're canceling each other out. And at about 68 hertz, we can see that the port is doing most of the output. Now, if we go back to VAX, we can see that the frequency response looks something more like what we'd expect from an actual driver. Now, this cabinet is quite small and the port is quite short, so it's obviously tuned too high. But that's not really the point. The point is that we can see what is going on here. So this is the frequency response, and this is the summed response. So what if we wanted to see the response of just the driver or just the port output? To do that, I'm going to go back to AKABAK. I'm going to go to the Observations tab. I'm going to just copy this radiation polar. I'm just going to right-click it and click Copy. Now I'm just going to paste it twice. And I'm going to call this one rear, excuse me, not rear, but port output. And here in range, I'm just going to remove elements 12. This means that it's only observing the output of the port, or the output of diaphragm back, which is what's coming through the port. So I'm just going to click Apply, and I'm going to do the same to this one, except in this case, I'm only going to look at the front element. So this is going to be output front. Click Apply. And now if I run the processing again, just the spectrum, and I open this, here we can see this is a very typical port response, right? Here we have the output of the port. We can see it's tuned to, yeah, around 70 Hertz, maybe little bit higher. And we can also go to the output front here, and here we can see the output of the driver. And as expected, we can see that the driver output is quite reduced around the port resonance. But in either case, we can see that the driver rolls off pretty smoothly, and really the same for the port. They roll off quite smoothly, but when they sum together, they are out of phase, and the end result is a rather violent roll-off. I really do hope you found this useful. This was just a simple introduction to how you can simulate a vented cabinet in AKABAK, and also how you can use the how you can couple lumped elements to the BEM model to get more accurate frequency response results. Thank you very much for watching.